Okay, so this PowerPoint will go over some basic properties of solutions. Before you watch this, you should open and either print off or look at your solutions definitions so that you can take some guided notes, because that will be a good guide over what we are going to be going over in this video. So first of all, I would like to define a solution. And if you see the abbreviation SOLN, that is the abbreviation for solution. So a solution is just defined as a homogeneous mixture. Back at the beginning of the semester, we classified matter, and we said that all matter is either a pure substance or a mixture. So pure substances are either elements or compounds. Everything else is a mixture. And mixtures can be either homo or heterogeneous. Heterogeneous means that they have a non-uniform composition. So think of a chocolate chip cookie where it's not uniform. You can't say that you're going to get exactly the same amount of dough and exactly the same amount of chocolate in every single bite. Homogeneous mixtures do have a uniform composition. And they have a uniform composition at the molecular level in a solution. That's what makes a solution so unique. Solutions always are made up of two parts. The first part is called the solute, and that's the substance that's being dissolved. The second part is the solvent, which is the substance that's doing the dissolving. So we have the solute and the solvent, the substance being dissolved and the substance that's doing the dissolving. In many of the solutions that you encounter in your everyday life, water is going to be the solvent, because water is a very common solvent. But as this table illustrates, you can have solutions of any composition. So for instance, when you take a carbonated soft drink or carbonated seltzer water, which is popular right now, that's a gas dissolved in a liquid, and the solution is still a liquid. So it's possible to have any phase dissolved in any other phase. These are just some common examples of different solutions. So now we're going to go through some properties that all solutions have that make them kind of unique from other types of mixtures. So first of all, again, the definition of a solution is that it has a uniform composition at the molecular level. So its distribution is uniform. And think about this: if you made some Kool-Aid and you made a pitcher of Kool-Aid and you mixed it until everything dissolved, so you don't have any leftover sugar or mix or anything like that, and you poured it into 8 glasses, the composition of glass number 1 should be identical to the composition of glass number 8. Solutions do not separate upon standing. So if you buy something that says shake well, it is not a solution. Solutions cannot be separated into components by filtration. So you can't filter a solution and separate the solute and the solvent. For any possible solute and solvent, you can make many different solutions. So you think about some sweet tea. There's not just one concentration of sugar that you can put in sweet tea. You could add 1 teaspoon and make one type of solution, or you could add another teaspoon of sugar and make the same solution, just of a different composition. Solutions are almost always transparent. That means you can see through them. And a solution is a homogeneous mixture. That means that even though it's uniform at the molecular level, it can still be separated into its components in a physical way. So you don't have to do a chemical reaction to separate out a solution. Now, like I said just a minute ago, many of the solutions that you will encounter are going to have water as the solvent. And that is because water is a great solvent. Water is sometimes known as the universal solvent. Because water is a very polar molecule, So if you look at the water molecule over here, here's my, sorry, I didn't mean to advance the slide. Here's the water molecule. So we know that the OH bond is polar and that the electrons are slightly closer to the oxygen than they are to the hydrogen in that bond. And so the oxygen becomes partly negative and the hydrogens become partly positive. So that's why water is a polar molecule. If you look at the crystal, this would be something like sodium chloride or table salt. So you have the positive sodium ions, which are yellow, and the negative chloride ions, which are green. So you have a water molecule, and the negative end is red, and the positive end is white. So the negative oxygen can pull that positive sodium out of the crystal, and the positive hydrogens can pull that negative chloride out of the crystal. There's that force of attraction. And so what you end up with is a positive ion surrounded by the negative sides of water, and you have a negative ion surrounded by the positive sides of water. Those ions then are referred to as hydrated ions. So if you look at that in equation form, any ionic solid that dissolves in water is going to split up into ions. And those ions then will be hydrated, meaning that they are surrounded by water. We know this AQ means aqueous or dissolved in water. So when a substance is aqueous, it means that the ions of that substance are dissolved in water. Now the process by which this occurs is called dissociation. Association means to come together. When you associate with someone, you're usually meeting that person and having an association. Dissociation means to break apart. So when an ionic substance dissolves in water and it breaks up into ions, we say that it dissociates. And most ionic compounds will dissociate when you dissolve them in water. So when an ionic compound dissociates, it produces what's called an electrolyte solution. And an electrolyte solution is defined as a solution that can conduct electricity. The reason it can conduct electricity is because it has dissolved ions. And those ions are charged particles, so they can in turn carry a charge. So you have negative ions, which can perpetuate that negative electrical charge. Now you're all familiar, or I would assume you're all familiar with a very common electrolyte solution called Gatorade, or something, Powerade, Pedialyte. Those are all similar solutions. Gatorade was developed by the University of Florida, whose mascot is the gator, for football players. And what they did was they studied the composition of sweat, and they saw what ions the football players lost when they were sweating. And so they came up with a solution then that was the purpose of which was to replenish those ions that were lost when sweating, primarily sodium and potassium. Now there's also other not so good things that are in Gatorade, like sugar and artificial colors and some artificial sweeteners. But that's why Gatorade was developed, to replenish the ions that were lost during sweating. And Gatorade is a common example of an electrolyte solution. But anytime you dissolve an ionic compound, and if it dissolves, it forms an electrolyte solution. So one way to test for whether a solution is an electrolyte solution or not is to put an apparatus that looks like this, and it's got two electrodes coming off of the light bulb, and then a power source. So if you turn on the power source, if the circuit is completed because the electrodes can pass a charge between them, then the light bulb will glow and it's an electrolyte solution. So something like sodium chloride, when it dissolves in water, would be totally split up into positive sodium ions and negative chloride ions. In this solution, the light bulb is glowing, but only slightly, because this would be something like HF, hydrogen fluoride, which when it dissolves in water stays mostly as hydrogen fluoride. You see the H's and the F's are still connected. There's only one H plus and F minus. So there's a few ions. The light bulb will not glow very brightly. In the last example, you have something like sugar. Sugar dissolves in water, but sugar is not ionic, so it cannot conduct electricity. It can't carry a charge. So the definition of an electrolyte is just a substance that can conduct electricity. Now, for the next part of this slide, or the next part of this unit, we are going to be talking about how we make saturated solutions and how that affects how we can. So let me start that over. For the next few slides, we're going to be talking about factors that affect how much of a substance can dissolve in a certain solvent. That's called solubility. Before we talk about solubility, though, we need to know what saturated is. So I want to explain how we can make a saturated solution. So I'm going to draw a beaker, or if you're not familiar with a beaker, think of it as a glass, which I'm not a great artist, but we're going to put the water in the glass. And let's say we want to make a solution. We want to dissolve some sugar in this water. So what we would do is we would add some sugar into the water, and we'd stir it up until all of the sugar dissolved. And you'd keep repeating that process over and over and over again until finally you got to a point where no more sugar would dissolve. And you're going to have some sugar that didn't dissolve laying on the bottom of the glass or of the beaker. The solution that exists above that then is called a saturated solution. And I'm not going to write that out because it's hard to write with this tool, but that is a saturated solution. Okay? Because you know it contains as much as can be dissolved. So to make a saturated solution, you keep adding the solute until no more will dissolve. You have a thin layer of undissolved solute on the bottom of your glass or your beaker or whatever, and the solution above it is a saturated solution. So the definition of a saturated solution, sorry, I'm trying to get to back to the PowerPoint. Okay, there we go. The definition of a saturated solution is one that contains the maximum amount of a solute that'll dissolve at a given temperature. Now, solubility is that amount, that mathematical amount. So solubility is defined as the actual amount of solute that dissolves in a certain quantity of solvent to produce a saturated solution. And a lot of times if you look up solubilities of things, it'll tell you it's this many grams in 100 grams of water. That's solubility. So solubility is the actual amount, whereas saturated is just the type of a description of the solution, and it contains the maximum amount that it can. So now that you know what solubility is, we're going to look at three things that affect solubility. The first one is called like dissolves like. The second one is temperature, and the third one is pressure. And like dissolves like is a saying that will help you to remember the first one. So let's go through each of these. So like dissolves like refers to polarity. Substances with similar polarities will dissolve in one another. So if you've ever worn or know somebody who wears nail polish, you know that nail polish cannot be removed by soap and water. Okay, nail polish is not soluble in water. That's because water is a very polar substance and nail polish is not. So to dissolve nail polish and remove it, you have to use nail polish remover, which contains acetone. Acetone is not very polar, so it can dissolve the nail polish. If you've ever observed Italian salad dressing, there's an oil layer and a water layer, and they don't really mix because oil is nonpolar and water is polar. So like dissolve like means that polar dissolves polar, and we include ionic in that because ionic is like almost an extreme example of polar, and nonpolar dissolves nonpolar. Now another common example of that are certain types of vitamins or medications. So you take something like vitamin C, and you can take a large amount of vitamin C without doing any kind of harm, because any vitamin C that's not used by your body is just going to be taken up by your kidneys, and then you're going to excrete it when you go to the restroom. So extra vitamin C is going to leave your body quickly because it's water soluble. Other vitamins like vitamin D, for example, are fat soluble, and so they will build up in the fatty tissues of your body, and you don't want to take too much of them, because if you have too much buildup, you could then you could have some poisoning. But they build up over time in the fatty tissues of your body, and then as you continue to take them, you're just depleting that buildup, replenishing that buildup as it's depleted by your body using those vitamins. So that's a common example of like dissolves like. The next factor affecting solubility is temperature. And I want you to pay close attention to this first statement. So the effect varies, and it must be determined experimentally. All right, so you can't just say that for every 5 degrees you're going to see an increase of 5 grams. That is not true. We're going to make some generalizations in this slide and in the next slide. And in this slide we're going to see that the solubility of a solid generally increases with an increase in temperature. So all of the lines on this graph that go up are actually solids. But again, their slopes are not uniform, so not all solids experience the same increase in solubility when you increase temperature. Take sodium chloride, for example. Sodium chloride is this brown line that looks almost straight. So at 0 degrees Celsius, which would be this part of the line, the solubility of sodium chloride is about 36 grams in 100 grams of water. If you go over to 100, the solubility only goes up to about 40. So that's only about a 4-gram difference in going from 0 to 100. If you look at something like this light blue line, which is potassium nitrate goes from 15 or so at 0 way up to 150 as soon as you get to about 70. So obviously that's a huge change, much larger than the change in sodium chloride. So the bottom line is you can't just make generalizations about amounts, but you can say that most solids will have an increase in solubility with an increase in temperature. Now for gases, the opposite is true. Most gases exhibit a decrease in solubility with an increase in temperature. And this is important for animals that live in water, like fish. Fish breathe oxygen that's dissolved in the water. So if the water gets too warm, the amount of dissolved oxygen will go down and the fish will suffocate. There won't be enough oxygen in the water for them to survive. That's why when a power plant is close to a lake and is putting water that it's used to cool the reaction, like a nuclear power plant uses water to cool the reaction, it can't just dump that water back into the lake, because what would happen is it would increase the temperature of the lake and you'd have a massive fish kill right by the plant. So they have to actually cool the water before they put it back into the lake or into whatever body of water it's going into. So that's temperature. For solids in general, the solubility goes up. For gases, it goes down. For liquids, you don't see much of an effect. Like I said, liquids are usually either soluble or they're not. Like dissolves like would be the biggest factor for liquids. The last factor that affects solubility is pressure. And what happens is pressure does not have much of an effect on the solubility of liquids or solid solutes, but it has a large effect on the solubility of gases. So if this is a container that has water and there's a gas in it, if you want to make more of the gas dissolve in the water, you can increase the pressure. Increase the pressure by pushing down on this plunger, and it will actually force more gas to go into solution. This is described mathematically by a law called Henry's law, which says that the amount of gas dissolved in a solution is directly proportional to the pressure of the gas above the solution. And a common example of this, or a common application of this, is a soft drink. If you've ever opened up a container of a soft drink, a bottle or a can of soda, you hear that popping or that fizzing noise as soon as you open it, because soda is bottled under very high pressure, several times atmospheric pressure. And when you open the top, you release that pressure. And so now the carbon dioxide that was dissolved is going to escape. And that's what the bubbles are, little bubbles of carbon dioxide that are leaving because the pressure of carbon dioxide above it has gone down. And so that's an application of Henry's law. So if you want to keep your soft drink fresh, you would put the cap back on so that the pressure goes back up as gases can't escape. And then you could put it in the refrigerator because gases are more soluble at cool temperatures. So those are the three factors that affect how much will dissolve. Like dissolves like, temperature, and pressure.